All right, well, since it's time, our second talk today, it's my pleasure to introduce Zoe Wyatt from King's College London, who will be telling us about global stability of spacetimes with supersymmetric compactifications. Zoe, please.
Cool, thanks very much, Martin. And thank you to Martin and the other organizers for the opportunity to give this talk. I really appreciate it. I just hope I get to visit Harvard in person one day. So today I'll talk to you about stability of spacetimes with supersymmetric compactifications. And let's say the broad goal is to understand the stability of spacetimes that arise in string theory and supergravity. Okay, so theories of quantum gravity. And everything I talk to you about today is based on these following three papers. So there's an earlier one from the start of my PhD, a more recent one, which is joint work with Lars Andersson, Pieter and Shing-Tung. So thank you to, I think they're all attending at the moment, so thank you very much. And also at the end, I'll try and tell you a little bit about a paper with Shijie Dong, who's just started a tenure track job at SUS Tech in southern China, which is actually related to these. Okay, so luckily I speak on Friday of a general relativity conference, so I'm not even going to write down the Einstein equations, but as we've seen so far, there are many explicit solutions to the Einstein equations. The simplest such one being Minkowski, and in today's talk, I will always refer to Minkowski or its metric as eta, okay, with the mostly plus sign convention. Okay, so I just want to set that notation. Other solutions are things like Schwarzschild. We've also got de Sitter. And the topic of today's talk is that a product spacetime. So here I take the Cartesian product of Minkowski with what we call an internal space, okay? So a compact Ricci flat Romanian manifold. And these are wonderful solutions. We hope that we can use them to describe physical phenomena that we see in our universe, but a very valid concern is that they all have a very high degree of symmetry. Okay, perhaps not so much this part here, but there is a high degree of symmetry going around. And so a very natural question to ask is whether these could ever be realistic models for a universe which is obviously dynamical. And so this is let's say the starting point in the research that I take, which is that of the initial value problem in GR. And so thankfully we've had lots of talks in this direction. But I've just got a little picture here, I guess inspired by Maxime's beautiful artwork yesterday. I've got some pictures myself. And so the premise that we have here is that the physically relevant spacetime should be stable to small perturbations under the Einstein equations. I mean, shocks may form, and certainly in the talk by Jared Speck, we saw that it is possible to have situations of shocks which could describe physical phenomena. Okay, I'm definitely not saying that can't happen, but let's say this notion of stability to small perturbations is very much what I'm interested in. And so our starting point is to suppose we have some initial slice here, sigma naught, and we've got some data, some known data, and we just add some small epsilon perturbation to it. Okay, I'm obviously not being very specific, but you could just think of that little bump there as being the perturbation that we add. And then we want to see what happens as we evolve forward in time. And I just want to emphasize that I think two interesting cases can happen. The first is that we go back to the background solution here, G naught, that we started from. But it is also possible that you evolve in a moduli space. Okay, so it is also possible, let's say, that you evolve to some G lambda where lambda is near 0. Okay, and lambda could be some parameter, like let's say the Kerr mass or something like that, Schwarzschild mass. Okay, so this is let's say possible under the assumption of small data, these kinds of phenomena can occur. And it's nice to remember probably the first known example of an unstable spacetime, which was Einstein's static universe, and this was obviously why he threw it away as a cosmological solution instantly, was because it wasn't, he could see that it wouldn't be stable under perturbations. Okay, so there's something a little bit obviously subtle going on in all of this, is that I'm talking here about evolution in time. I've got t here going to 1, t going to infinity. What on earth can time mean in a theory that is manifestly independent of the coordinates that we use? And so to make sense of this initial value problem, we need to specify coordinates. Okay, we need to break the gauge invariance. In this conference so far, we've seen lots of different ways to do so. I guess we've had lots of double null gauges. And what I'm going to choose in this talk is something called the wave gauge. Okay, so what do I need? So I need a reference metric E hat on my manifold M, and this gauge condition selects coordinates, which I call here Y gamma, such that the difference of these two Christoffels between G and this reference metric vanishes. Okay, so we have the vanishing of this quantity V gamma. It's the difference of two Christoffels, which actually transforms as tensor. So this is a well-defined object on your manifold, and so you can use it to indeed break the coordinate invariance. And I think probably the simplest example to give is that if your manifold emits global coordinates, okay, like Minkowski, then you can just define this reference metric to be the flat, to be eta with respect to these global coordinates. So then these components, these Christoffel components vanish. And so this wave gauge condition precisely reduces to, let's say, the more commonly known condition, which is that of harmonic gauge or de Donda gauge. Okay, and you might have seen it written in this form that I just put in the red box, also this equivalent one here. Okay, so it's just a slight generalization of that very well-known gauge that we have there. And so if we assume that our space-time also satisfies this gauge condition, then the equations of motion reduce to what I call the reduced Einstein equations. And the crucial point now is that these are a system of quasi-linear hyperbolic equations. Okay, so because they're hyperbolic, you can do lots of things. You can show that we have local in time solutions, we have Cauchy stability. So you can really kind of very much get your hands dirty with these equations. I just want to mention, though, that this is a system of quasi-linear equations for G mu nu. Okay, and so that means you actually need a slightly larger set of data if you want to use the theory of hyperbolic equations. Okay, and so in fact, the process of constructing that extra data is exactly where the constraint equations come in. Okay, so something that I haven't mentioned in here is that you also need some constraints in order for it to be sufficient to study just the reduced Einstein equations to guarantee that you also get a solution to the full geometric Einstein equations. Okay, and so this is based on, but this is the work of Schocker-Bruhar and later with Garoch. And so telling us that we have a local in time result, telling us that we do have a local well-posedness result. And so the question that I come asking now is that of global stability. Okay, and so now I want to show global in time well-posedness for these coordinate fixed Einstein equations. And obviously now it makes sense to talk about time, given that I've fixed my notion of time. Okay, and what do we assume? We assume that of initial data. Okay, we assume small initial data rather. Okay, so these are, I've put now here two very well-known results that a few people have mentioned already in the conference so far. So the first of these is that Minkowski, okay, the trivial solution to the Einstein equations, is a stable solution to the vacuum Einstein equations, and also if you couple it to a massless scalar field, okay, to a wave equation. And the first work in this direction used a different gauge to the one I've introduced. That's work of Christodoulou and Kleinemann. But perhaps the more relevant work today is the one that used harmonic gauge given by Lindblad and Romanian in the early 2000s. And I've tried to put these two results here, let's say these two different theorems, just so you can kind of see the differing ages. Okay, so kind of how long the different time periods that these happened in. Okay, so kind of, let's say this is in the 90s and this is in early 2000s. Obviously the work of Hintz and Vachi uses quite different methods, so that's kind of why that took a bit longer. But then in the second result here, I've got that Minkowski is a stable solution to the Einstein Klein-Gordon equations. Okay, and that notably took a lot longer. Okay, so the first work in this direction, again in the harmonic gauge, was that of Lefloc and Ma. Okay, we've got work in a maximal slice gauge by Wang, and also Fourier methods by UNESCO and Pauseter. Okay, but let's say a big difference that's happening here is just that it took, like a decade or a bit longer for this later work to come out, for these later works to come out, and that's, it's just all we've changed is the mass of the scalar field. Okay, so I just want to tell you a little bit about why that is the case, because it's actually going to be relevant for the product spacetime. This I am telling you all this for a reason, I promise. So we're talking about Minkowski, so we can consider the wave gauge or the harmonic gauge. Okay, so that reference metric I can fix to be eta, and I can write this the unknown variable g in terms of the perturbation. Okay, so I can write I can define h to be the unknown variable minus the background. Okay, so we can think of H now as being small. And the reduced Einstein equations simplified to, as we've seen already, a quasi-linear system of wave equations. Okay, so here I've now got the flat wave operator, so minus dt squared plus the Laplacian. Okay, and your hope is, of course, that if the initial data is small, that the linear behavior will dominate. So what is the linear behavior? In R1 plus 3, it's very, very rigid, okay, and it's governed by something called Strong-Huygens principle. So if we have a solution to the linear wave equation, and here I've put compact data, then we have a fundamental solution, okay, and we very well understand what happens to this solution, okay, so we see that it propagates out on light cones. We have a finite speed of propagation. We have a domain of dependence argument, all this kind of thing. And how does the equation decay? Okay, so this here is three-dimensional, so we do have decay, and the solution actually decays like 1 over t. Okay, and this is not integrable. And so this is actually a critical decay for nonlinear problems. Okay, so you hope that your linear behavior will dominate in this quasi-linear setting, but you've got very slow linear decay. Okay, and so this can cause issues. And indeed, this is as well known. There's work of John who showed finite time blow up for solutions to this following semi-linear wave equation. Okay, so where I just have some kind of naively a nonlinearity that should be naively very friendly, okay, but indeed this solutions to this equation blow up in finite time, which does make you worry about the full Minkowski setting. And so indeed there was work of Shoko-Bruhat that suggested that the wave gauge would break down, okay, so understanding perturbations of Minkowski in this gauge would not, let's say, work out. And so this is why, you know, it's very impressive, this work of Lindblad and Romanian, because they showed that that is not the case. And one of the kind of essential ingredients in their proof, you know, not just their proof, but more broadly in vector field methods, is the availability of symmetries. Okay, so they make use of Minkowski symmetries. And so that means they consider a collection of vector fields that generate the Poincare algebra of Minkowski. So these are very much tied to the isometries, Minkowski spacetime. So here we have you know, DDT, we've got the generators of spatial translations. Here I'm using this notation Z to denote the Lorentz boosts. Okay, and we've also got here what's more commonly written as omega AB. Okay, so the generators of rotations. And these vector fields commute with the wave operator. Okay, and so if I have a solution to a wave equation, let's say psi, I can produce another solution, okay, to a slightly different wave equation. Okay, but if f were 0, then indeed I would go from one solution to another solution, okay, of the linear wave equation. And Minkowski also has conformal symmetries. And so this is something that I guess Yakov mentioned yesterday, which I refer to as S. So this is the scaling vector field. This obeys a different commutation relationship with the wave operator. Okay, and so in fact, we get this identity here. So if I have a solution psi to the wave equation, then I can still produce a solution to another solution to a wave equation, S psi, but you see here the right-hand side is slightly different. Okay, so if f is 0, then linear solutions generate new linear solutions. And so this distinction, the reason why I've put S, this scaling vector field, in red is because its behavior manifestly changes when you consider a Klein-Gordon equation. Okay, so just to remind you, the Klein-Gordon equation is written here for a scalar field psi of mass m, and the minus m is matching the sign convention that I've chosen here of mostly plus. Okay, and you can only commute this equation with the first set of vector fields. Okay, so with the translations, the rotations, and the boosts. Okay, and so in particular, we cannot commute, let's say, the linear equation here. So just suppose I had the linear Klein-Gordon equation. If I commute through with the operator S, then I pick up, you know, this part here is 0. That's great, but I pick up a first order term. Okay, and so this essentially just means that you cannot use this scaling vector field, and that kind of breaks a lot of your analysis estimates. And so in particular, you can't commute S through the reduced Einstein-Klein-Gordon equation. Okay, and so let's say, just heuristically speaking, the reason why these later papers on the Einstein-Klein-Gordon equations took so long is because you had to kind of develop a whole machinery that that allowed you to do away with this scaling vector field S. Okay, so that's a notion of, let's say, broken symmetry is what I would view that as. So now let me tell you about product spacetimes. Okay, and I will relate this to the broken symmetries just then. So the idea of a product spacetime actually goes back to Kaluza in the early 1900s, and his idea was to take the 15 components of 5-dimensional vacuum general relativity and encode or extract from those 15 components the 10 unknown components of 4-dimensional general relativity, the 4 unknown components from Maxwell's theory of electromagnetism. Okay, so that's the 4 components of the electromagnetic vector potential, and there'd be one missing component, which I guess would just have to be a scalar field phi. Okay, so this was just to kind of emphasize, this was really quite advanced at the time, because these were the only 2 known fundamental forces of nature in 1919. Okay, they didn't know yet about the strong and the weak force, so it's really quite wonderful that he was trying to develop a unified theory of gravity and electromagnetism without just kind of artificially putting it on the right-hand side of the equations of motion, of the Einstein equations, rather. And so Klein then realized a bit later that the best way to achieve this unification was through a product spacetime where the extra dimension would be small. Okay, so the simplest Kaluza-Klein product spacetime is the following here. So I have Minkowski across a circle. Okay, so d theta squared there, or it could be a flat, let's say a flat d-dimensional torus. And I guess I'm denoting this high dimensional metric here by g circ, but I will refer to that again later. Okay, so what would a stability for a Kaluza-Klein space look like? So if you consider the wave gauge as before, where your reference metric is actually your background solution, and then you write out the perturbation H, okay, you consider the equation of motion with the perturbation H, then the reduced Einstein equations give you this following system here. And very much like the Klein-Gordon equation, we have a broken symmetry. Okay, so the linear part of the principal part is this bit in brackets, sorry, and we get this new Laplacian term appearing here coming from the circle, and much like the Klein-Gordon mass, this breaks your symmetries, and so you also cannot commute with the scaling vector field. Okay, in exactly the same way you cannot commute, and obviously there's a whole bunch of other problems, like the fact that you've got lots of different derivatives, including derivatives in the circle direction. Okay, so that makes it a bit more complicated, and so the first PDE results in this direction assumed initial data that essentially regained this lost symmetry. Okay, and so what you can do is you can consider perturbations. So you can consider perturbations that are independent of the circle direction. Okay, so d theta of H would be 0, and so that would just kill off this part, which is breaking your symmetries. Okay, now this condition, okay, on these types of perturbations was actually known in the physics literature under the name of the cylinder condition. So let me just tell you a couple of things about the cylinder condition and where it comes from, let's say. So if you suppose that your circle S1, okay, has radius r, then you can do a Fourier expansion in this periodic coordinate. And so let's say your 5-dimensional spacetime. Okay, so your higher dimensional spacetime. All right, we can write it in terms of these Fourier modes. Okay, so we now pick up this mode number L. Okay, and we've got this exponential factor here involving this periodic coordinate theta. Now, if you substitute this expansion into the Einstein equation, it's obviously an absolute mess, but you can look at what happens to leading order, okay, where we had this differential operator that I mentioned earlier, and to leading order, you get this part here, okay, so you get the wave operator minus L over R squared times these different components. And so the idea is that, okay, so this is exactly a mass. Okay, it's got the right sign to be a mass, and so we've got an infinite tower of Klein-Gordon masses. And the idea is that if this radius r is very, very small, then this mass is very, very large. Okay, or these masses become very, very large. And so at low energies, you will not be able to probe them. Okay, you will not be able to perturb them. And so we'll only perceive the L equals 0 mode at low energies. Okay, just remember that this is I know it sounds very vague when we talk about this in maths, but you know, the reason why the Higgs boson took so long to find is because it was very heavy. Okay, so if something is very heavy, it takes a lot of energy to probe it. Okay, so this is kind of what's happening here. And so the idea then is that you keep only the zero mode, and that exactly yields the cylinder condition. Okay, so there's the fact that your high dimensional metric only depends on the Minkowski coordinates. Okay, I've got here Minkowski indices. And so you can actually take this assumption, okay, take the cylinder condition and deduce from it an effective lower dimensional theory. Okay, so you need to take an ansatz. Okay, so here we've got our high dimensional metric G, and you rewrite it in terms of a 1 + 3 dimensional metric G tilde, a vector potential A and a scalar field phi. These all only depend on the Minkowski coordinates. And you get here a lower dimensional theory. Okay, so this lives in 1 + 3. It's not exactly how I've written it there. Okay, it just takes, you know, it's quite a long system of equations. But the key thing that I'd like you to note is that you cannot consistently set the scalar field to be 0 and have a non-trivial vector potential A. Okay, so we don't see massless scalar fields in physics. We see a massless vector boson. Yeah, we see the photon. But we don't see a massless scalar field. So you would, in principle, like to set phi to be 0 and just study gravity and electromagnetism. But actually, in this ansatz, you can't do that. Okay, so this is really coming from the fact that there's no natural constraint on the radius r. And so in principle, you can really scale it to be whatever you want. There's no a priori reason that it would be small. And so, as I said, that the first PDE results assumed this cylinder condition, okay, assumed this reduction on the perturbation. And so this is one here from my thesis. So I showed that the Kaluza-Klein spacetime is asymptotically stable to these toroidal independent perturbations, okay, so S1 independent perturbations under the vacuum Einstein equations. And I say here asymptotically stable because you start with a Kaluza-Klein space, you've got some radii, and you could imagine that you put in some matter, okay, and it disperses away, but you could imagine maybe somehow that you get like a memory effect that somehow, you know, some radius actually, it doesn't go back to the one that you started with. And this result shows us that at least to toroidal independent perturbations, that does not happen. Okay, so you don't evolve within that R moduli space, which, yeah, I think is somewhat interesting. And then there's another result where this changes. So you can consider the Milne universe. Okay, so this is a vacuum cosmological solution. Okay, in particular, it's an expanding solution to the vacuum Einstein equations, but there is no cosmological constant. So Milne is an interesting model to study cosmological behavior within. And I'm sorry, I haven't put on here, and I really should have, but I guess I can say in words that the Milne is known to be a stable solution to the vacuum Einstein equations due to work of Lars Andersson and Vince Moncrief, work in 2003 and then later work in 2011. Okay, so you know that this is a solution to the vacuum Einstein equations, and so you can also then just take a Cartesian product with a torus and then study stability of this to toroidal independent perturbations. And let's say this Cartesian product that you form, you can call a cosmological Kaluza-Klein spacetime. Okay, and Brandin, Feynman, and Kronecker studied the stability question here, but again, subject to the cylinder condition. Okay, so they took this spacetime and they showed that it is stable to toroidal independent or S1 symmetric perturbations, but they actually get evolution within the R moduli space. Okay, so there is some scaling because of the coordinates that you use, but they do actually get that the metric, the flat metric that you have in your torus that you end up with is not exactly what you started with. Okay, it's like a slight perturbation from the background one. So you do actually in this instance get evolution within this moduli space, which I think is quite interesting. But now we obviously see more than just electromagnetism in the standard model, okay, or what we see at the Large Hadron Collider. And so string theorists typically then like to consider other compact Ricci flat Romanian manifolds. Obviously, your hope is that your effective lower dimensional theory will exactly give you this SU2 times U1 non-abelian gauge theory that we see to describe the other fundamental forces. So that's so like the building blocks that you use then, let's say to construct this theory, are more complicated Ricci flat Romanian manifolds, and the prime example of this is of course the Calabi-Yau manifold, Calabi-Yau threefold, and also many other geometries that you can use. And so from Minkowski, so what I now consider is I take Minkowski and I take its Cartesian product with one of these more complicated geometries, and this is now a solution to the vacuum Einstein equations. Okay, now it's also a solution to supergravity, and it's also subject to string corrections. Okay, so there actually are other effects that this spacetime could be undergoing, but just from a starting point, what we're interested in is just the behavior of this spacetime as it evolves under the vacuum Einstein equations. Okay, which is something that is a good starting point. Okay, so let's talk about the PDEs. Okay, so if you want to consider the stability of a geometry of this type. So maybe I'll just put it back up here for one more minute. It's very weird when I can't see people, if anyone's confused or something. So maybe I just also briefly mention that the higher dimensional spacetime here is G-circ. It's not so important with the indices, but I've tried to be consistent. So we've got spacetime indices, which are Greek. I use these lowercase Roman letters here to denote Minkowski, so eta here, ij, and then I also allow for compact indices, which are denoted by capital Roman letters AB. Okay, so this is the background. I'll tell you some conditions coming up on the compact space, but for now this is the background, and so we can just immediately ask what do perturbations of this background look like? What are they governed by? The equations of motion. And so we now consider the wave gauge, again, where we set that reference metric to be the background one, G-circ, and we write, once again, H as the perturbation variable, okay, variables. And the reduced Einstein equations become the following. Okay, so we've got here a lot of new terms, and so I guess this is what I'm trying to see here. Let me just emphasize, there really are a lot of new terms if you're not just in the case of simple Kaluza-Klein theory. Okay, so in particular, we pick up this term here in blue, we pick up a background Riemann curvature component, okay, which if you're not on something which is not flat, then this could be non-trivial. We've also got nonlinearities on the right-hand side, which can involve quadratic derivative nonlinearities, okay, which is what is very well studied thanks to work of Lindblad and Raniatsky, things like the weak null condition. But we can also actually have undifferentiated quadratic nonlinearities that come about from contraction with the background Riemann curvature tensor. Okay, so these are very different to what has been studied before. So I just want to focus on this part that I've put here in blue. Okay, so this is this linear part here. Okay, and so this extra term coming in is H alpha beta, you should think of as being the quasi-linear part. So let's just ignore that for now. And we can focus on these blue parts for different cases of mu and nu. Okay, and so if you take one of these indices to be in the Minkowski direction, okay, then the Riemann curvature tensor ends up collapsing onto the Minkowski part, so you get 0. Okay, and so you just get back the wave operator plus the Laplacian on the Calabi-Yau. Okay, and actually you don't get these order h squared nonlinearities. You only get these derivative ones. Whereas if you then look at the case where one of these indices, sorry, HAB here. Okay, so the indices here are in the compact directions, then you get something very different. Okay, so we get this wave part, we get the Laplacian, but we also now get this contraction with the Riemann curvature tensor. Okay, and we also have these terms on the right hand side. So this differential operator that I put in underline, I denote by LK or minus LK. So that's what I'm going to talk about on the next slide. And so this is almost the Lichnerowitz Laplacian. Okay, so the Lichnerowitz Laplacian evaluated at a Ricci flat metric, which is what we're in. And so this is how we define it. So this operator LK, which acts on symmetric 2 tensors H. So this is just exactly what I had on the previous slide. And we define a Romanian manifold to be Romanian linearly stable okay, if this following L2 inner product is non-negative, okay, for all symmetric two tensors. Otherwise, we say it is unstable. So now this condition it naturally arises in geometric analysis, okay, so in Romanian theory. So if you study the Einstein-Hilbert actional for general relativity in the Romanian setting, and you take the first variation, you get Ricci is equal to 0, and then you take second variation and you consider that at a Ricci flat metric, then you want to look at, let's say, a certain sign condition on the second variation, okay, to maybe it's positive or negative, whichever way it needs to be. And so if you decompose your space of tensors, let's say symmetric tensors, into certain pieces, one piece that comes, so there's, let's say, 3 orthogonal parts of this decomposition. The first 2 parts end up, you get sign condition that you want. That's kind of known from, let's say, powerful elliptic results. The last piece that you need to get a sign condition on is exactly what is given here in the condition of Romanian linear stability. Okay, so it's exactly this operator here that you want to be bigger than or equal to 0. Actually for all TT tensors, but let's not worry about that for now. And so this is a very kind of powerful result, in particular because this operator LK, it's self-adjoint and elliptic on a compact space. And so this condition of Romanian linear stability gives you a lot of control. Okay, so it tells you that you have a discrete spectrum. This condition very much tells you something about its minimum eigenvalue. Also tells you that you have a finite dimensional kernel. Okay, so something that I think we don't know as much in, let's say, in the general relativity community, or at least I didn't when I came to this project, is that all known examples of compact Ricci flat Romanian manifolds are in fact Romanian linearly stable. Okay, the only known examples that fail this, that are unstable, are non-compact. Okay, and the reason for that is this quite general theorem of Dai, Wang, and Wei, because all known examples of compact Ricci flat Romanian manifolds satisfy the assumptions of this theorem, which says that the manifold has a spin cover that admits a non-zero parallel spinor. Okay, so some kind of a spinorial object, which plays a very important role in string theory and supergravity. Okay, and so this is a very, let's say, large class of geometries then that we consider, okay, that satisfy this condition of Romanian linear stability. And this is what we call in the paper a spacetime with a supersymmetric compactification. Okay, so we take Minkowski and we take its cross product with one of these spaces, one of these compact Romanian manifolds. Okay, from this theorem. Okay, so that is the space now that I'm interested in. Okay, so this is the G0. And so this is the theorem that we proved. Okay, so this is let me just talk us through this. Okay, so first of all, let n be bigger than or equal to 9. Okay, which is obviously something we hope to improve in future. A space-time with a supersymmetric compactification, okay, so what I just had on the previous slide, is asymptotically stable, okay, under the vacuum Einstein equations, to perturbations that are as compactly supported as the positive mass theorem allows them to be. Okay, so they're exactly equal to Schwarzschild times the product space outside of a compact set. We have a appropriate notion of smallness. Okay, so the Schwarzschild mass term must be small, and we've obviously got some L2 norms and a certain number of derivatives that need to be sufficiently small. And so under this assumption, we get global existence, and also the solution satisfies the following pointwise bounds. Okay, so this is the theorem that we showed. So let me now just give you some comments on this theorem, and then hopefully just a little bit of a discussion about proof. So some comments are, okay, so firstly, there is a positive mass theorem that's known for these kinds of product geometries. That's, let's say, given in a paper by Dai, but there might still be questions to consider there. Now, I said this really is a technical restriction. So this restriction in the data that we say is compactly supported as the positive mass theorem allows. You know, it probably saved us 80 pages in the paper. I don't know, a lot of pages in the paper. I think it's a technical restriction. I would expect it to be. Certainly the first work of Lindblad and Minkowski also, assumed this kind of assumption, as also the work of Lefloc-Marr. Their first result was under this compact support restriction. But I really must emphasize that it prevents moduli evolution. Okay, so you could imagine that you kind of have some perturbation of your background, and then you evolve to Minkowski times a nearby Calabi-Yau. Okay, or a nearby kind of special holonomy manifold, and this very much prevents that from happening. Let me also mention some nice new work by Huneau and Valcoux looking at existence of Kaluza-Klein initial data. Okay, so in the special case of Kaluza-Klein, they're very much looking at constructing non-trivial classes of initial data. Okay, so another comment is you may have heard of the work, very famous work of Ed Witten. Okay, so in 82, he showed that the Kaluza-Klein spacetime is semi-classically unstable. Okay, and this is his so-called bubble of nothing solution. And you might say, kind of, how does it relate to our stability result? Because it's very much his instability result, what he considered. And the key difference here is that his bubble solution had a different kind of topology. Okay, so his initial slice topology there was R2 times S2. Okay, and so, the fact that his perturbation kind of decayed into this bubble solution is because he argued that under some semi-classical process, a topology change like that is allowed. Okay, and so, that's very well and good in semi-classical theory, but we're looking really in the classical theory, and so that kind of topology change does not happen. Okay, so in our case, let's say we'd be looking at Rn times S1. Okay, so something different. Some more comments. So if you look at the linearized PDEs, okay, so looking at the linearized equations of motion, we get this following system here where I've just got some asterisk symbol for the whatever the contraction is there. And so we could actually decompose solutions to these linearized PDEs using, say, eigenfunction projections. Okay, let's say depending on the index that you're considering, but in terms of the Laplacian or the Slick-Narevitz Laplacian. And schematically, you would end up with a system, an infinite system of equations like this. So you'd have one equation, which is the wave part, and then you get an infinite set of Klein-Gordon equations. And the key part now is that their masses would be real masses. Okay, it's not somehow that you get an imaginary mass and then you get in a Klein-Gordon equation where the mass is the wrong sign. That's what Romanian linear stability gives us. Okay, it tells us that these masses have the right sign. And so you could in principle study this kind of decomposition. It would be quite messy, but it has actually been done in kind of various contexts. I'll mention work of Metcalfe, Sogg, and Stewart looking at waveguides, and perhaps very closely related to this is work of Ettinger, okay, looking at a semi-linear PDE in a product spacetime. And so he took this approach. And in fact, you could use this approach to show linear stability for our SUSY spacetimes, okay, all the way down to n bigger than or equal to 3. Okay, so at the linear level, you can go all the way down to that. Okay, so that's some comments. And then the last comment I want to make is in relation to conjecture of Penrose. Okay, so this is kind of loosely formulated in various places. And he argued that certain perturbations of these product spacetimes would lead to a trapped submanifold. And by some kind of appropriate extension of his singularity theorem, we would get incompleteness. Okay, so the kind of perturbations that he was particularly worried about were perturbations H that only depended on this very small compact space. And he was worried that somehow they would focus so much energy that you would end up forming a trapped submanifold very, very quickly. And then I guess it wasn't entirely covered by his singularity theorem as originally written, but it certainly was covered by later work by Galloway and Senevilla, okay, where they kind of wrote down these singularity theorems and various conditions that would give you incompleteness. And I think kind of the key thing or the key difference that's happening here is it's what you deem to be an allowable perturbation. Okay, so in the assumptions of our theorem, we had localized L2 perturbations. Okay, whereas in some sense, what Penrose is considering here is unlocalized L infinity perturbations. Okay, so if you were to take this perturbation assumption and just put it into, say, the assumptions of our theorem, you will get some small perturbation, okay, of size epsilon naught times the volume of your compact space. And then you need to integrate that over Rn, okay, which gives you infinity. Okay, so this would not be an allowable perturbation according to us, but if you were to, dictate that you had some fall off and, some norm was then finite, then it would fall into our class. And just to substantiate that a bit more, so there's some later work of Cipriani Senovia, and possibly also in the work with Greg, where they gave conditions of not just incompleteness, but also completeness. Okay, and just to give you an example from this second paper, they studied warped product spaces. Okay, so Minkowski times this flat torus with some warping factor F. Okay, and they, using, let's say, these conditions from Galloway and Senovia, they found conditions on this warping factor that would give you completeness. And they, for example, found this condition. Okay, so completeness if F is globally near 1. Okay, and this kind of assumption is, a priori, we can assume this. Okay, in small data stability questions, this is something that we would fall into immediately. Okay, so I think it, yeah, so it's a bit different there, let's say. Okay, so now let me tell you some ideas from the proof. Okay, gosh, okay, running a bit out of time. So, I should have written the equations again, but hopefully you've seen them about 3 times now. So we've seen that they are wave equations with a different kind of an additional part to them. Okay, so let me just tell you a little bit about wave equations and then the methods that one uses and how we adapt those methods. Okay, so the linear wave equation, thanks to, let's say, Noether's theorem, has a conserved energy. Okay, so this functional E, okay, which is an integral of the square of the derivatives of your solution over Rn, is conserved in time, okay, assuming some appropriate fall off at infinity that you can do. Okay, so this is a conserved quantity, and we call it an energy precisely because this first term here is exactly a kinetic part, and the second part here is a potential part. Okay, so that's why we call it an energy. And now the good commutation properties, okay, that I talked about several slides ago, imply that from a solution to the linear wave equation, I can construct another solution to the linear wave equation. Okay, so here I've now put in an appropriate number of spatial derivatives. Okay, and this is also a linear solution, and so we also get another conserved energy. Okay, that this other functional is also conserved. And so you can use this idea to get a uniform norm in terms of data. Okay, so we can control, let's say, the solution pointwise in space by a Sobolev estimate. Okay, I can embed it into Hn with an appropriate number of derivatives, which I'm not specifying here, but are roughly the spatial dimension over 2. Okay, and then this Sobolev norm, well, this is exactly controlled by my energy functional, okay, at some time t. But then this energy functional is conserved in time. Okay, that's what we have on this line above here, and so that means that its value at time t is exactly its value at time 0, and this energy at time 0 I can write in terms of initial data. Okay, so we're able to control the solution, I say, in terms of initial data. So this is one starting point, but we'd also like to get a bit more control in the solution, and so this now follows ideas of Kleinemann from the 80s and his vector field method. So we use the commutators, the set of commutators that I mentioned earlier, okay, which here I denote by gamma. And we form from that a symmetry boosted energy. So now I allow for the same energy functional from before, but I can take any kind of combination of these vector fields up to some appropriate order k, okay, whatever that might be. And again, by the good commutation properties, okay, by the solution to the linear wave equation, that this symmetry boosted energy is also conserved. Okay, and now we do the same Sobolev estimate, but because we have considered now vector fields that have weights in t and x, we can actually show decay. Okay, so in particular, we can show, let's say, that the derivative of our solution psi, okay, pointwise, I can control it by some decaying factors. So t here to the minus n minus 1 over 2, and I can have a t minus r here to the minus 1/2, once again times an energy, okay, at some time t. All right, so these factors here are very much coming because we've now included t and x weights in our commutators. All right, and these, again, if this energy is conserved, well, then I can just replace this t here by 0. And so I now get a decaying factor times some quantity involving the initial data. Okay, and so this is good. We're recovering, let's say, linear decay rates, like what we'd like to see. Let me just emphasize also that in here we have a change. The decay rate depends on your spatial dimension. So here we've got an n factor and n factor. And we also have improved decay as you move away from the light cone. Okay, but I don't really want to go into all these details here, but let's just emphasize that obviously if you've got more spatial dimensions, you've got more space to move, so your perturbations, their amplitude will decay faster. Okay, and so that's what we see for the linear wave equation, unsurprisingly. Okay, so now this is, let's say, an approach for wave fields, but I've emphasized a lot that Klein-Gordon fields have to be treated differently, and this is what took a long time to develop in the literature. And what do we need to avoid? We need to avoid this scaling. We need to avoid this scaling vector field. Okay, and so to do so, one approach is to consider hyperboloidal slices foliating your spacetime. Okay, so instead of taking slices of t is equal to constant, we now take slices of s is equal to a constant, where s is a hyperbolic time coordinate. Okay, so it's square root of t squared minus mod x squared. And so in the future, the interior of the forward light cone, okay, we use hyperboloidal coordinates. So we have a time coordinate s, and we have a coordinate on the hyperboloid, which I denote by y. Okay, now one of the big restrictions when you do this assumption is that you very much have to assume compact data, and if you want to remove compact data, you have to do a lot of patching. Okay, so we don't do that. We don't need to worry about that patching in the same way. So so that makes it a bit easier, but very much now we're looking at these hyperboloids, okay, which I've drawn here. So here's one hyperboloid, here's another, and we've got some data, and that is propagating forward, okay, in time. And so we now have the vector field's tangential, okay, to the hyperboloid. I denote by ddya. Okay, and so these are actually just some rescaled version of the Lorentz boosts. Okay, so so this is just a new foliation, and you can look at what the conserved energy becomes. And this is what you get here. So your conserved energy is now involving an integral on the hyperboloid. We now get some weights involving s, okay, and dy, okay, coming from the fact that we're on a hyperboloid now, not a constant t slice. It's still conserved up to some appropriate data assumption, and we can now allow for a mass term. Okay, so this is schematically the same, but we now only need to use a subset of these vector fields in the Sobolev estimate. Okay, so if we consider this subset Z here, which only needs to consist of the time translations, the spatial translations, and I guess here I've put in the Lorentz boosts and the rotations, but you don't even need the rotations under compact support. You can now prove the following kind of estimate. Okay, so you can now get a control on the value of the field psi, a certain number of its derivatives, in terms of this conserved energy, En, okay, at some hyperbolic time s, okay, and if this is conserved, well then I can replace s there just by s naught, let's say your initial time, okay, and so we now get some decay rate in terms of initial data. Okay, so for the case of Klein-Gordon fields, this gives you better decay estimates. Okay, you'll note here that we've got this n over 2 part. Okay, so that's improving on that n minus 1 over 2 from before. But very much here, you've got this factor of n. Okay, so you only get this improved rate for Klein-Gordon fields. But you do get the same estimates for waves that we had from before. Okay, so you can kind of look at how S over T behaves in different regions of space-time, and you can match up with the original decay estimates that we had. Okay, so this method, okay, of considering hyperboloids and Sobolev estimates on hyperboloids dates back to work of Kleinemann and Hormander in the context of waves by Tataru, and then more recently by Lefloc and Marr. Okay, so this is now like the ingredients that we all have to kind of do our proof. Okay, and so the first thing that we have is that we have a very novel energy functional. Okay, a lot of the, let me just emphasize that the PDEs, the linearized PDEs that we study, very much have a tensorial nature. Okay, they involve a Riemann, sorry, this is Riemann here. They involve a Riemann curvature component. Okay, so you have to contract on something. You can't, this equation doesn't make sense for scalar fields, is what I'm trying to say. Okay, it really only makes sense for tensorial equations. And so you need to then introduce an energy functional that's adapted to that fact. And that's what we do. So we have this energy functional here, which involves a term very much coming from these linearized PDEs, coming from this background Riemann curvature part. We have, as before, we have some kind of Minkowski derivatives, as we would expect. And now we also pick up these two new pieces here coming from the compact space. Because of the lack of commutation, because we can't commute our equation with the scaling vector field, just like for the Klein-Gordon field, we evaluate this energy functional on hyperboloids. Okay, so that's where that's coming in. But for this energy functional to be useful in any meaningful way, it needs to be non-negative, and this is exactly where we use the condition of Romanian linear stability. Okay, is in that point there. Okay, so this is our energy functional. You need to boost it using some appropriate vector fields. Okay, so I'm not going to comment about that. But then we also need to get a Sobolev estimate. So now we can't use the scaling vector field. Okay, we cannot use that as a commutator in the equation. We don't quite have a Klein-Gordon field, though. We don't quite have a Klein-Gordon equation, so we can't use the homogeneous Sobolev norm, which means that we don't control our field in L2 at the level of the energy. But we can at least use a standard Sobolev estimate. Okay, and so inspired by an argument of Hormander, okay, in his textbook, we show the following Sobolev estimate here. Okay, so some pointwise bound on H, where we now get some T decay. Okay, and we guarantee that we pick up a term here, which is a Minkowski derivative. Okay, and so this then we can naturally bound by the energy. Okay, now obviously the energy is not conserved here because we have nonlinearities, but I'm not going to talk about that today. But the key thing to note is this decaying factor here, it does have a loss. Okay, so the decay factor that we get is n-2/2. And just for comparison, for a wave, you get n-1/2, and for Klein-Gordon, you get n over 2. Okay, so this is certainly not optimal in that sense, but a nice kind of rescaling argument that gives us this Sobolev estimate. And so then to conclude the proof, we take this spatial dimension large enough so somehow you don't have to worry about nonlinearities. Okay, you lose decay in various places by using Hardy estimates, and so somehow for the whole bootstrap to close, we need n bigger than or equal to 9. Okay, so that's where that comes out. The dimension of the compact space just comes out in the regularity of the data. It's just something that comes in your Sobolev estimates. The Sobolev n that I've been talking about. Okay, so we very much conjecture that we can lower the dimension to n equals 3, but to do so we need to be a lot more refined than what we're doing. So that's things like looking at weak null structure and your nonlinearities. We have in our Sobolev estimate, we very much merge together wave and Klein-Gordon behavior. Okay, and we kind of take the intersection of the two. But really to go below this, we're going to have to split between kind of wave-like behavior and non-wave-like behavior. Okay, Klein-Gordon-like behavior. And let me just mention it would actually be quite nice to get some more structure requirements on this compact space. Okay, so we only really require this Romanian linear stability condition. And one thing that you'd like in this whole kind of program of research is to be able to identify certain product spacetimes that are stable and certain ones that are not. And so for that, we'd really like to get some kind of condition on this compact space that, you know, gives you stability. And if you don't have that, you know, that's not good. So let me just, mention that. And so then to conclude, I just want to talk about, so I said here on this slide, we need to differentiate between zero and non-zero modes. And so this has actually recently been done in some really wonderful work by Huno and Stingo from last year. And so let me just tell you a little bit about this. I don't have many minutes left, so I'll try and try and hurry up. So they considered the Kaluza-Klein case. Okay, so it's a simpler setting, but they considered two scalar functions, phi and psi, living on R1 plus 3 times S1. Okay, and they satisfy some quasilinear wave equation. Okay, but their idea very much is that you could think of one of these variables here as acting like the metric component h theta theta. Okay, so the structure that we get here is, exactly what I was showing you on one of the earlier slides looking at Kaluza-Klein stability. And so, I haven't stated their theorem, but let's say they show global existence and decay. And one of the key ideas behind their approach is they don't consider the infinite. Well, okay, let me phrase it this way. They consider projections onto the different eigenspaces. Okay, so they take let's say the massless projection and the massive projection. And in doing so, you get this infinite system of wave and Klein-Gordon equations. Okay, so here they have an equation for the wave field, and then they get this infinite system here for the Klein-Gordon field. What they do is actually a bit smarter than that. Instead of having to study an infinite system of Klein-Gordon equations, they just consider the original variable minus the massless part. That's one of their variables, and then the other variable is just the massless part. Okay, so they only have two kind of components in that sense to study. But one thing that does arise because of the quasi-linear nature of the Einstein equations is that these Klein-Gordon components here pick up a variable mass term. Okay, so they pick up, you can think of this as kind of the mass of some Klein-Gordon equation, and this mass varies in some small sense. And so this is something that I've studied with Shijie Dong, is problems of this type. So looking at systems of wave and Klein-Gordon equations where you have certain nonlinearities that you can bring to one side of the equation and treat as a variable mass Klein-Gordon equation. Okay, and so somehow the decay estimate that we show in this paper is very much what Huno and Stingo were inspired by. But yeah, there's actually lots of systems. So this system here you can study, and this is what we did, but there's lots of other systems that you can't. So there's kind of lots of open questions with wave Klein-Gordon problems. So let me just finish here. Sorry, I realize I've only got 2 minutes left. So this is what I've showed you. And I think if you take one thing away from today's talk, I hope it's that you realize that we can consider these product geometries and that this internal space breaks the symmetries in a way that gives you effective wave and Klein-Gordon-like pieces. So thank you very much for your attention.
Thanks, Zoe. All right, any questions?
I have a question. Could you quickly comment again on this dimensional restriction, where that comes up?
This n bigger than 9.
Yeah,
so it's very much from the fact that the linear wave equation decays faster in higher dimensions. And so somehow as that dimension goes up, you've just got more and more dispersion coming in, which is just kind of washing out your nonlinearities. So it's very much that, like, to prove the stability of Minkowski space, let's say in 4 spatial dimensions and higher, is far easier than 3 spatial dimensions. Somehow 3 is very critical for nonlinear problems. And so the way we've treated the estimates in this problem, we ended up needing n bigger than 9 for now.
All right, well, if there are no more questions, let's thank Zoe again for a lovely talk.
Nice talk to you.
Thanks, thank you so much, Yao.
Yeah, thanks.